Ratio test is one of the convergence tests used to determine convergence or divergence of an infinite series. Let's denote the limit of the absolute value of the ratio between consecutive terms as L. If the value of L is less than 1, the infinite series converges absolutely. If the value of L is greater than 1 or tends to infinity, the series diverges. If the value of L is equal to 1, the convergence or divergence cannot be determined using the ratio test alone, and other convergence tests should be employed. We learned that the given series converges. Let the general term be denoted as an, where an is 1 over n squared. The next term, an plus 1, is as follows. Let's find the limit of the absolute value of the ratio between two consecutive terms. After simplifying the complex fraction and taking the limit, it becomes 1. The given series is a harmonic series, which we learned diverges. Let the general term be denoted as an, where an is 1 over n. The next term, an plus 1, is as follows. Let's find the limit of the absolute value of the ratio between two consecutive terms. After simplifying the complex fraction and taking the limit, it becomes 1. As observed in these two cases, if the value of L is 1, the convergence or divergence cannot be determined using the ratio test alone. Please remember this point. The ratio test is not a solution for determining convergence in all cases, but it is particularly useful for series that converge rapidly. Series involving factorial or exponential terms fall into this category. Let's consider the following example. If we denote the general term as an, where an is 2 to the power of n over n factorial, then an plus 1 is as follows. Let's find the limit of the absolute value of the ratio between two consecutive terms. After simplifying the complex fraction using the exponential rule, it can be expressed as follows. N factorial can also be rewritten as n plus 1 times n factorial. Common terms cancel out in the numerator and denominator. The fraction simplifies further. The limit approaches 0. As we learned earlier, if the value of L is less than 1, the series converges. Let's solve the following example. If we denote the general term as an, where an is n factorial over n times 3 to the power of n, then an plus 1 is as follows. Let's find the limit. After simplifying the complex fraction, it becomes a bit complicated. Simplify again. Common terms cancel out in the numerator and denominator within the absolute value. The fraction simplifies further. The limit approaches infinity. Therefore, the series diverges. Here are guidelines for the 8 convergence-divergence tests we've learned so far. First, perform the nth term test for divergence. Since there are multiple testing methods, students often overlook the nth term test for divergence. However, it's important to check this test first. If the limit of the general term is not 0, the series diverges. Second, consider geometric series. Although it's not exactly a divergence test, it frequently appears in exams. If the absolute value of the common ratio r is less than 1, the series converges. Third, use the p-series test. Since it has a special form, it's easy to recognize. If p is greater than 1, the series converges. Fourth, apply the alternating series test. If the positive part of the general term satisfies two conditions, the series converges. Fifth, utilize the integral test. If, when the general term is applied as a function, the function is continuous, positive, and decreasing, and the improper integral converges, then the series also converges. Sixth, employ the ratio test. It's advantageous for series involving factorial or exponential terms. If the limit of absolute value of the ratio is less than 1, the series converges. Seventh, utilize the comparison test. If a larger series converges, a smaller series converges, and if a smaller series diverges, a larger series also diverges. Eighth, use the limit comparison test. For all positive general terms, if the limit of the ratio is finite and positive, then either both converge or both diverge. The order presented above is for reference only. It does not necessarily imply a strict sequence. Please be aware of this. See you next time.